and fuel cells, and this for, of course, the reason that we, as you may know, have big plants in our energy system. So we want to switch off nuclear power plants and at the same time want to reduce CO2 by percent till 2050 in our energy system, and that requires new technologies. Okay, so if you talk about hydrogen, there is of course traditional petrochemical ways to make hydrogen, and you all know this. There is reforming of gases, and here, and there's partial oxidation, and you can make it from coal and from heavy oil, and you can make it also from biomass. The processes from all these starting materials are very similar. You can either do a conversion with water, and you would call this steam reforming, like shown here for methane, which is an endothermic process, or you do partial oxidation. And in both cases, you get mixtures of CO and hydrogen, and after water-gas shift reaction, as my colleague said, you would have hydrogen. And the key thing is that burning hydrogen in a fuel cell or in an engine produces water as the only byproduct. Of course, if you do reforming in your fuel cell, then you also produce CO2, but from the reformer and not from the fuel cell process. And of course, there is another possibility, and this is to produce hydrogen from electrolysis using renewable electricity from wind and sun. There are different technologies that are very quickly developing and reaching the state of commercial use now. So Siemens, for example, has announced a megawatt electrolysis which is installed now in a German city. And the prices become more and more reasonable. And of course, in principle, that gives you now access to a kind of carbon-free energy system, because you can split water by electricity, somehow store, transport the hydrogen, and then burn the hydrogen again in a fuel cell. And to be honest, I think that scientists around the world, given global climate change and all these issues, will probably not stop before they have not somehow fulfilled this mission. So split water by electricity and recombine hydrogen with oxygen to form water in order to release energy. And this is a carbon-free energy system, which of course is not real yet, but I personally believe will be more and more important in the next 10 to 20 years. Now, what is the problem? Hydrogen itself has a very high gravimetric storage density, 3 times higher than fuel, 33.3 kilowatt hours per kilogram, but a very low volumetric storage density, only 3 watt hours per liter, while diesel has 10 kilowatt hours per liter. So hydrogen storage and transport is about getting the density of hydrogen up, and you can do this by liquid, by cryogenic hydrogen, by compressed hydrogen, by adsorption onto materials, by metal hydrides, or by chemical transformations. And I will focus on chemical transformations because I think this is the only way to really store hydrogen in large quantities. This here needs high pressure or low temperature, so it's a bit difficult from the infrastructural side and also for large amount storage. This, of course, here, the two methods here need fancy materials, and also they have solids involved, which is always difficult for large applications. And here, what we call now in Germany power to X, we have two technologies. The one is hydrogenation of CO2 and use of methane, methanol, and Fischer-Tropsch products in today's infrastructure. And the other one, which is a bit more recent and might be not known to everybody here, is the so-called liquid organic hydrogen carrier system concept. And I show you here what this means. It's basically a reversible hydrogenation, dehydrogenation cycle. The whole thing works in cycle. You typically start with an aromatic compound that you hydrogenate in exothermic reaction to an alicyclic or heteroalicyclic compound. Typical storage densities up to 7.2 mass percent. Then this you can store like fuel because it's an organic liquid with chemical bound hydrogen. And then whenever you want to release the hydrogen, you run a dehydrogenation reaction where you need some heat intake and hydrogen comes out. And that hydrogen forms then electricity in a fuel cell, and you can take the excess heat of the fuel cell to run the hydrogenation, dehydrogenation process. And so The key story with this LOHC concept is, first of all, that you use the infrastructure for today's fuels, because these are liquid fuel components, that the whole thing runs in cycles, so we do not burn the hydrocarbon. This is the key message. We only use the hydrocarbon as a deposit bottle for hydrogen. So we bring hydrogen on the material, we release hydrogen from the material, and the whole thing runs in cycles. We talk about 1,000 cycles per organic molecule in order to store the hydrogen. Yeah? And at the end of the day, this is a CO2-free storage and release of energy. And this also makes it different from some concepts where you have CO2 hydrogenation, because even you take CO2 and hydrogenate it, whenever you use the energy, you will release CO2, so the balance is neutral, but the local emission of CO2 is not. So the question is, what type of liquid can fulfill this? You need something that has a high hydrogen capacity, that is reversible, that is fast in its kinetics of charging and decharging to get power in your system. It must be extremely selective, so side product formation is almost forbidden, otherwise the 1,000 cycles would not work. And the whole thing should have a broad liquid range, should be compatible to today's infrastructure, and of course should be also safe from the toxicology point of view. And this is, after 5 years of development, our favorite system. It's a dibenzyl toluene and perhydrodibenzyl toluene. And you may wonder why this is our favorite system. I come to this on the next slide. First of all, I want to show you the principle once again. So we take this multi-aromatic compound, charges with hydrogen. In this case, it's 6.2 mass percent. This can be stored like diesel, if you like, and carried around. And then whenever you need the energy, you release the hydrogen in a dehydrogenation process. So what is so special with this material? First of all, 6.2 mass percent of hydrogen is not bad. All the components are liquid down to -30. The boiling point is 360 to 390. This is 360, this is 390. So it's very easy to produce very pure hydrogen because of the large boiling point difference between hydrogen, -253, and the carrier, +360. So you get hydrogen in 5.0 quality directly out of the system. Yeah? It's available as industrial heat transfer oil. This is very important. And some of you may know Malotherm, which is a 50,000 tons per year product in heat transfer. And because it's known since the 70s of the last century, there's an extensive safety data sheet that tells that dibenzyl toluene is not carcinogenic, not mutagenic, and not toxic. In fact, it's much less toxic than diesel and fuel. And so we can transport it without having to label it as hazardous material, which is very different from fuel and diesel. It's full compatible with the fuel infrastructure because it's a pure hydrocarbon. And maybe that's interesting for you. The price is between 2 and 5 euro per kilogram, depending on the scale. So we talk about something like 3 times the price of ordinary fuel, but we do not burn it in one application, but we will load and unload it 1,000 times with hydrogen. And so from the technology, it's much more similar to a compressed gas bottle. And what you see here is a 300 bar gas bottle from Linde, and in front you have the liquid 25 kilograms that has the same content of hydrogen than the gas bottle, but of course it's much safer because it's a high boiling organic liquid. So to make a long story short, in our institute, we develop this technology, we develop catalysts, we develop reactors, we develop systems. And 2 years ago, we have found our own spin-off company, Hydrogenous Technologies. If you're interested, you can go to the website and see much more details on the technology. So the product of this company is 20-feet containers that are mobile energy systems, if you like. So we can, for example, take hydrogen from an electrolyzer or from any industrial source of hydrogen and load the material in this hydrogenation reactor. And here you have the tanks. The one tank here is 1,000 liters or 2 megawatt hours. So 2 megawatt hours storage capacity in 1,000 liters of liquid. compare this to a battery, and then you see it's a quite effective way to store renewable energy. In this other container, you see the dehydrogenation unit, which is this reactor here, the tanks again, and some cooler here to separate the liquid from the gas. So what are the application scenarios? And I selected application scenarios that might be of interest for a global conference. The first one is off-grid energy storage. So today, if you have a mobile phone transmitter station in the desert, you have a diesel generator and you have a truck that brings diesel to the diesel generator, and then the diesel generator is producing electricity. Even so, in this place, you have the whole day sun, and you could very easily have photovoltaics and a storage system, and then this transmitter station would never have to see a truck bringing diesel to it. And this is exactly one of the application scenarios. So you have your receiver, you make electricity the day directly to charge your transmitter, but during the night you take the material that has been charged over the day with hydrogen, release the hydrogen, and deliver the energy out of this storage system. Another thing that is quite interesting is hydrogen logistics. In fact, as you will see later, hydrogen in compressed gas bottles is a very lousy way to produce, to distribute hydrogens. And one idea that we have basically in Germany, but it could also be interesting for the United States and other countries, is to take hydrogen produced from these renewable energies and distribute it over today's fuel system to bring it to a filling station where hydrogen is filled in the future at 700 bar to operate this Toyota Mirai. The one or the other of you may have heard that Toyota is very much going towards hydrogen mobility, and in Japan at the moment a lot of hydrogen filling stations are built simply because of the CO2 footprint of that type of mobility. And if you want to have hydrogen mobility, the key question is, how does the hydrogen come to the filling station? And this is our way that we propose. And you can very easily show economically that this kind of transport of hydrogen is much more effective than compressed hydrogen or liquid hydrogen, because you get much more into your truck. The truck is much more cheaper, and the risk and also the maintenance costs are lower. So while the liquid hydrogen can transport more, it is very expensive, and it cannot go through tunnels, and it is not allowed to pass certain towns, and so on and so on. So this is a very effective way of hydrogen transport. And now comes a final example for this community here. You are all in oil and gas, and you know that there's a lot of flared gas from production sites where the gas comes out with oil but cannot be used. And I take the quote of Russell the first day, "Don't waste the waste." So what we have developed is a way to transform methane, waste methane, into a storable and transportable form of hydrogen. The concept is very simple. You take a classical reformer, very rough, a classical water gas shift, and then you go with the gas mixture that comes out of the water gas shift directly onto your LOHC system that takes selectively out the hydrogen, and everything else goes back into the burner that runs the reformer. And by that, with basically 3 boxes, you can convert excess methane from those locations into a transportable fuel where hydrogen is stored, and you can bring this hydrogen to a filling station, and you get a very high price at the filling station for this type of hydrogen. So we think economically it's a great way to upgrade stranded gas to hydrogen at filling stations in California or Germany, where people are ready to pay something like $10 per kilogram of hydrogen. So this is the technology. Of course, if you have something new and people don't know it, there are many questions, and sometimes the question is a bit unfair, but let us see. So what are the mostly asked questions here? Is the hydrogen quality of the released hydrogen good enough for fuel cell? We can say yes, because we have made many fuel cell trials and operations. Is the overall efficiency good enough? We believe yes. Main losses are in the electrolysis in the fuel cell, but if you can make use of the heat losses of the fuel cell in the process, that's very efficient. So total efficiency of 80%. if you take heat as a product into account as possible. And then about the stability of the system, so we guarantee for customers 100 to 200 cycles, but our development is definitely 1,000 cycles. And of course, you can always ask the question whether they are better molecular systems, but we believe that the dibenzyl toluene, because it's known to the industry, it's cheap, it's very stable, it's a heat transfer oil, so it's made for high temperature resistance, is a very good choice and can be used for commercialization of the technology. So this is my final quote, maybe for you to think about it. The former oil minister of Saudi Arabia said in 2000, the Stone Age did not end for the lack of stone, and the oil age will end long before the world runs of oil. So what the bottom line is, if scientists find better technologies, there's no need to wait for the moment when no oil is present. I think there are many countries on Earth where you have a big potential in wind and sun, and if you transform this to hydrogen, store and transport it to the right place, you can add something to a green and sustainable world. Thank you very much.